So summary here. We stated that the mechanical extensive variables are time averages over the microscopic state. And then we use the ergodicity principle to replace the time average by an ensemble average. Right? We defined what ensembles are, and they are all the quantum mechanical eigenstates consistent with the boundary conditions, where the boundary conditions are specified by the extensive variables, right? Just like in thermodynamics. Most important thing is the postulate of equal a priori probability, which states that all microstates with the same energy have the same probability, which means in the microcanonical ensemble, they all have the same probability. And then I gave an initial derivation of the canonical ensemble. Canonical ensemble being one where the outside temperature is fixed, so the energy can fluctuate. And there we found that the probability depends on the Boltzmann factor. So it's the exponential of minus beta the energy divided by Q. Q is the partition function, which will play a central role in thermodynamics. But for now, you can think of it as the normalizer of the probability. Okay. So today what we're going to do is a much more elaborate derivation of this again, because it's a more classic derivation, and it will allow you to do any general ensemble. Okay. So the method that we'll be using is called the method of the most probable distribution. It's pretty much described. It's a very classic derivation. It's in every statistical mechanics textbook, and it's definitely in Macquarie. And what I want you, so this is, I want to warn you, this gets kind of like many steps, looks like extensive math, but try not to lose the forest through the trees or the trees to the forest, because conceptually it's actually very straightforward how you get the probability distribution. So what you do is you take your canonical system. So what I'm drawing here is a canonical system, and you make many replicas of it, which together you make form a microcanonical ensemble. So basically, I repeat my system many times, put it together, and together I force them into a system at constant energy. So the green box is a microcanonical ensemble. At some energy E total. But inside, the black boxes, they are my canonical ensemble. And the number of copies inside here, so I'll call that A. There are A copies of the canonical ensemble. And I can always send A to infinity, in which case the fluctuation of one canonical ensemble in here has only an infinitesimal effect on all the other ensembles. So its copies are acting as a heat bath for any specific ensemble. And what we're going to do then is try to characterize how many of the canonical ensembles are in a given energy state. So what you gotta, when I talk about an ensemble, right, sometimes I'm going to talk about the canonical ensemble, which is the one that I have replicated a lot. And sometimes I will talk about the large microcanonical ensemble in which they are all together. So the canonical system if I look at all the replicas, I can look at which state each of them is in and essentially make statistics of that, how many are in each given state. So let's say I know all the states of the canonical ensemble. I'll just call them 1, 2, 3, 4, etc. Right? They would each have an energy, E nu, which would be E1, E2, E3, E4, etc. And now what I'm going to do is in this large microcanonical ensemble, I'm going to count how many of them are in a given state. So if I have A1, that's the number, A1 is the number of canonical systems in state 1. A2 is the number in state 2, A3, etc. So you can think of this as an occupancy, right? How many of your canonical ensembles occupy a given state? And the total vector, I'm going to write as A bar, is this distribution, right? So the total vector, A bar, is this distribution, A1, A2, A3, A4, etc. Now there are constraints on the distribution. That the sum of the occupancies has to be the total, right? I've made large A copies, so all the occupancies have to sum to 1. And there's a constraint on the energy, that the energy of all the canonical copies has to sum to E total. So the other constraint is that the sum I, AI, EI has to be equal to the total energy of the microcanonical ensemble. So once you do this setup, you may want to think already about how you will get there, because conceptually the hard work is done here. We got to do a lot of math now, but think about what's going to happen here, right? If I take a given distribution like an A bar, no, not an A bar, take that back. Okay. If I take a given state of the microcanonical ensemble that satisfies these constraints, so each replica has a certain energy, and then I take another one where, I don't know, maybe this one has very high energy, this one has very low energy. What do you know about these probabilities?
They're equal.
Yeah, they're equal, right? Because I've embedded these, I made so many copies, I've made this total to be a microcanonical ensemble. So any distribution, any specific state of the microcanonical ensemble, which means basically any distribution of microstates has the same energy, because it's the same total energy, therefore it has the same probability. So which distribution is going to be the one that I observe? It's going to be this distribution here that satisfies these boundary conditions, but the distribution that has the highest multiplicity, right? That it has the highest frequency of appearing. And we're going to be back to combinatorics. So I'm going to go through the math, right? But this is essentially what's going on, right? So we've done this clever construction of cloning our system into a microcanonical ensemble for which we know the distributions. That means we know how energy can get distributed between the copies. That means we know the relative distribution of energy in a given copy, right? This is completely reminiscent to what we do in thermodynamics when we can't figure out equilibrium, right? So if you remember in thermodynamics, if we have a system and we don't know what's going on the boundaries, right? We can't sort of control the work or heat. We can't define it. We take a bigger system boundary. And then sometimes we say, well, that's closed. Just like we originally defined equilibrium of a system by looking at the internal equilibrium of the universe, which was by definition closed. If you look at that derivation back in thermodynamics, this is exactly the same concept. You always go back to a microcanonical ensemble, because in a microcanonical ensemble, every distribution has the same energy, therefore it has the same probability. So let's work that out now. I'm going to need a lot of board space today. So what do we know about the distributions? So each state of the microcanonical ensemble has the same probability because it has the same energy. Because you have the same energy. Now, what do we know about the multiplicity of a distribution? Right? If I assign a bunch of occupancies, I say I have 5 systems with energy 1, I have 10 systems with energy 2, etc. Then I know that the distribution is binomial, right? So the multiplicity of a given distribution is a factorial divided by the product of the small aj factorials. So technically, we know everything now, right? We know how this is distributed. So we could do things like, under these constraints, calculate the average energy in the microcanonical ensemble. But in practice, we have to make it a little simpler. So, for example, if I wanted to know the probability to be in a given state nu, now for the canonical ensemble. How would I write this? Well, the probability to be in nu would be the average of the occupancy for state nu divided by the total. And I can write out, how would I write out the average, right? So 1 over A, summing over all the possible distributions times the multiplicity of the distributions times the value of A nu in that distribution. And then normalizing by all the distributions. Right? I'm summing, right? The way I get this average A nu is by evaluating it in a given distribution. That's what I'm doing here, right? And then summing that over all the distributions and their multiplicity. So it's a classic probability calculation. So in principle, you could take this equation and you could calculate it under these constraints. And you could actually do that. But in practice, that's hard, and there's a simpler solution because of as you push A to infinity. So we're going to approximate this formula, but in the limit of sending a to infinity, it will be exact. And the reason is that in practice, the multinomial, right? This is going to be a multinomial. The multinomial is very peaked around its average or its most likely distribution. So if I plot the degeneracy as a function of a star, there's going to be some value of a bar star, which I'll call the value where the maximum occurs, where the degeneracy is the highest. And around here, you're, as you know, as we've derived before, you are Gaussianly distributed. So what happens is that as we send a to infinity, this Gaussian narrows. And you can convince yourself by looking at what we did the lecture ago, by looking at the Taylor expansion of the Gaussian and showing that its amplitude deviates as soon as you go away from the average, and it deviates like 1 over the square root of n, where n is the size of the system. So what we are going to do is we're going to replace this distribution. So we're going to replace WA, that distribution, by the distribution at the maximum. So rather than summing over all the distributions, we're going to say we're just going to take the maximum because it totally dominates this summation, and we don't have to do this summation. So what that means is we have to find, so what it means now is that our objective is find a bar star where WA is maximal. And you could tell, maybe you're going to tell me, well, I already know that, because if I have a multinomial, right? If I have a multinomial, where is it maximal? Where it's where all the buckets are equal. So in principle, I know that, except that the problem here is a little different, right? So in principle, all the coefficients AJ would be equal to maximize the multinomial, except that that solution would not satisfy the constraints. So the reason this is a little harder is you're not just maximizing the multinomial, you have to maximize the multinomial under these constraints. And so that's what we're going to do. Okay, let me start that here. So what we want to do is a constraint maximization of WA under constraint 1 and 2, right? Where the constraints come from the summation that you have to add up to the total number of systems, and you have to add up to the total energy. Since the distribution is a bunch of factorials, I'm going to maximize not the distribution, but the log of it, right? This is a classic trick by now. Since log is a positive function, if you take if you maximize the log of a function, you also maximize the function. And if you take the log, we can use Stirling's approximation. So really what we're going to do is, instead of W, we're going to maximize the log of W. And the way you do a maximization with constraints is that you use the method of Lagrange multipliers. So what the way we're going to maximize this, we're going to take the derivative with respect to each coefficient in the distribution. So we're taking the derivative dA nu, where A nu now can be any of the occupancy variables of the logarithm of WA. And then minus, and I'm going to take as Lagrange multipliers alpha for the first one and beta for the second one. So minus alpha sum I AI minus beta. Minus A total. And then the second constraint will be minus beta sum K AK EK minus E total. And that we will set to 0. And if we solve this, we will find the coefficient A nu that gives us maximum. We will, if we do this for every A nu, right, because we have to do it for every state in the system, we will find the distribution that has maximal multiplicity.
Excuse me, is the derivative over the entire expression or just the log WA?
No, you have to take the derivative of the whole thing, right?
Okay, cool.
What I was just going to say, when you take the derivative, and you also have to take the derivative, by the way, thank you, you reminded me, you have to take the derivative with respect to the Legendre multipliers, right? You also have to take d alpha equals to 0 and d beta equals to 0, right? But those derivatives give back the constraint, right? If I take the derivative of this with respect to alpha, I just get the constraint back. If I take the derivative with respect to beta, I get this constraint back, right? So this is sort of superfluous. I just get the constraints back, right? Yeah, you're right. I'm missing a bracket. That's what, here we go. Okay, so let's take the derivative of this. We're going to use Stirling on the logarithm. So let me do that on this board. You know, this is a derivation you really should do a few times yourself. There's so many gems in here of statistical mechanics that keep on coming back. So if you learn to do it, it'll keep on giving. Okay, so we're gonna use Stirling on LNW because WA is A factorial divided by. Now, I apologize for always using different dummy indices, but I hope you can handle that. KAK factorial. I think I called it I there or so, but it doesn't matter. It's a dummy index, right? Okay, so if I take the log of this, this is the log of A factorial minus some K AK log AK. Which if I now use Stirling on this, this is A log A minus A minus some K AK log AK minus AK, right? Make sure you get comfortable taking the log of things that are like x log x. We will do that hundreds of times, right? When you take the log of, when you take the derivative of this, then you retain the log. When you take the derivative of the log, you get 1 over AK, and so you get a 1. Okay, so let's take that derivative now. So if I now take dA nu, so here I have all the coefficients. So I'm now taking the derivative with respect to one of them. So most of this summation here will drop out. Right? Most of this summation over k will drop out. There will only be one term that survives. So if I take the derivative with respect to a nu, I get minus the log of a nu. This doesn't contribute at all to the derivative, right? Because it's a constant. And here I just pick out when k equals a nu. Minus 1. So that comes from this part. Then when I take the derivative with respect to the first Legendre, with respect to the first Lagrange constraint, I just pick up alpha, right? Because I have the sum here over all the coefficients ai. So I just pick out the one that's a nu, so that gives me a minus alpha. And when I do that here, right, when I take the derivative with respect to one specific coefficient a nu, that will pick out beta times e nu. So the derivative will be minus alpha minus beta e nu. And that has to equal 0. So we can do this for every value, for every nu, and these derivatives look all the same, right? So there's not just one equation like this. There are as many as there are energy states, except that the equation looks the same all the time. So the solution is the same. So if we solve this, we find that a nu, so the value of a nu in the most probable distribution is, I'm taking the exponential here, is e to the power alpha plus 1 times e to the power minus beta e nu. Right? That's by solving this equation and taking the exponential. And I don't like the alpha plus 1, so I'm just going to call that alpha prime. So what are we seeing here? Note that we're close to what looks like a Boltzmann probability, right? Except for a few things. I haven't figured out what the normalizer is, but normalizers are never hard, right? You just enforce that the total all the probabilities have to sum to 1. But there's another subtlety here, right? I kind of deceived you a bit. I called the Lagrange multiplier beta. So all I know here is that this beta is a Lagrange multiplier. I really cannot assume it's 1 over kBt. We will later show that it's 1 over kBt, which is why I've used beta. But nothing in this derivation so far is shown this, right? All this is sort of telling us that the probability is going to be proportional to the exponential of minus some constant times the energy. So let me first get rid of alpha prime. That's easy. Getting rid of beta, as you see, is going to be tricky. So the way I get rid of alpha prime is really just like by enforcing that the probabilities have to sum to 1, sorry. Okay. So the sum of all the occupancy variables has to be equal to A, right? So if I sum all these folks here, so that means that the sum over all the states I have dropped a sign here, right? This is e to the minus alpha. And so then this is e to the minus alpha prime. Not that it's important, it's just going to be a constant, but e to the minus alpha prime, e to the minus beta e nu. This has to equal to a. So then I can back out, right? Because this is a constant here. This is not dependent on nu, so this comes out of the summation sign. So what I get is that e to the power alpha prime is 1 divided by a times the sum over nu e to the minus beta e nu. And so what that means is that the probability to be in a microstate nu is the value of a nu in the most probable distribution divided by a total, and that is equal to e to the minus beta e nu divided by the sum over all microstates e to the minus beta e nu. So all I've done here is gotten rid of the prefactor, right? The term with alpha in. But this looks remarkable like what we've seen before. Again, this object here, the sum of e to the minus b eta, e to the minus b eta nu, this is called Q, the partition function. And while it looks like a dumb normalizer so far, what we will see later is that it takes a tremendously important role in all of statistical mechanics. So, the most annoying step that comes is the one that comes now, is to identify what beta is. It's I don't know what to say about it. It's not deep. It's just annoying. And I'm going to go through it once, but when I do other ensembles, I'm not going to do this step anymore. But I want to pause here for a second to make you see a few things. And you're going to get more opportunity to learn this. But where does the e to the minus beta e nu come from? You know, because this is going to be the thing that overwhelms all of physics and material science, all of statistical mechanics, right? That probabilities go exponentially with minus the energy. And again, we haven't done it yet, but we're going to identify that beta is 1 over the temperature. But so in the derivation, where does this come from, right? So you look back here, okay, this is where we set the derivative equal to 0, and this is where the minus beta e nu shows up, right? So where does that come from? We can go back to the thing with the Lagrange multipliers, right? It comes from the constraint on the total energy, right? That's where the e to the minus beta e nu comes from. And maybe that makes sense, right? If you solved this problem unconstrained, we know what the solution is, right? You know what it's erased now, but you know what the maximum of the binomial is. Is you fill all the buckets with equal probability. So what would the energy of a system like that be? In some cases, in many cases, it would be infinite, right? If a system has an energy spectrum that goes to infinity, right? Like particle in a box, the harmonic oscillator, we would be saying like we have to fill every state with equal probability. So our sum would go up to infinity, right? So the Lagrange multiplier is what pulls you back and says, no, I didn't give you infinite energy, right? I keep you at a certain total energy. And that's exactly where this comes from. And so to run ahead, what you're going to see later if we have other constraints on a system, right? Let's say I have a grand canonical ensemble, right? So if I have a grand canonical ensemble, then if I have a grand canonical ensemble, then this little box is going to be a grand canonical ensemble, so it can also fluctuate the number of particles. It can fluctuate the energy and the number of particles. But I'm going to do the same trick. I'm going to embed it. I'm going to make clones of it and make a giant microcanonical ensemble. I'm going to do exactly the same derivation, except I'm going to get another constraint, right? That if I add up the particles in all the subsystems, all the clone systems, I have to have a fixed total number of particles. So if I write this minimization, I'm going to get another term here. I'm going to get some minus gamma and then some sum over the distribution variables times the number of particles in each state minus the total number of particles. So when I then do my minimization, I'm going to get something that shows up here that's going to be like minus gamma, right, number of particles. And what do you think gamma will become? If beta is going to be 1 over the temperature, what do you think gamma is going to become? If I have, so now I'm going to get like, if I work through this probability, it's going to be e to the minus beta e gamma minus e nu minus gamma number of particles in K. It's going to be the chemical potential, right? So we're going to do this again. So don't worry about, I just wanted to show you that there's already a lot of depth and generality here. But one of the next lectures, I'm basically going to repeat exactly what I said. But I'm a strong believer that sometimes saying things twice makes it clearer. Okay, so now let's go to the hairy and messy and slightly boring derivation to figure out what beta is. I will try to hide my enthusiasm. I've never found any depth in this derivation. So if you do, please let me know. Then next time you can give it. Okay, I think we can erase the board now. So the derivation is boring, but the result will be splashing, smashing, or whatever. Jenyang, I think you should cue up drum roll music when we're done, because the result will be worthy of a drum roll. Okay, so how do we get beta? With a pen that writes. So here's going to be the strategy. We're going to develop relations. We're going to develop a relation between the average energy beta and some other thermodynamic quantity, which in our case will be pressure. And we're going to do that in StatMech. And then we're going to do the same in thermo, but for T. So between U, which is the average energy, T, and P, we're going to do that in thermo. And since we believe both to be true, that's going to give us a relation between beta and T. And that relation will, of course, be that beta is 1 over T. Let me first do the thermo one, since we're all so brilliant in thermo that we can do this. And then let's spend 5 pages on the StatMech one. Okay. For thermo, I'm going to use the first law, that du is TdS minus p dv. I am going to divide by, this is a good thing to do in color. I'm going to divide by dv and take this at constant n and t. So that goes away. And I can't do anything with the derivative of ds dv, so I'm going to use Maxwell on this. So this is equal to, as you now well know, to dp dt at constant v and n. So the derivative that I get is that du dv at constant nt minus t dp dt at constant nv is equal to minus p. And you could sort of argue, like, why this one? Well, I'll show you in a second, because the average energy, which is the internal energy, right, is easy to get in StatMech. I'll show you that shortly. And then taking things like derivatives with the mechanical variables is easy to get as well. So it turns out that this derivative will be quite easy to get in statistical mechanics. So is this one, though it's a little trickier. And so when we get those derivatives in statistical mechanics, we can kind of add them in and compare to this equation. The StatMech equation will look, I'm first going to give it to you and then prove it, will look like this. It will look that the average energy derivative with respect to volume at constant n and beta plus beta dt d beta at constant n and v is equal to minus p. So I haven't proven this yet, right? So this is thermo. This will come from StatMech. So I'll call this 2. And if we compare these, you will be able to identify, you can probably already do that now, that beta is 1 over kb over t, right, up to some constant. Just so the average energy and u is the same thing, right? I use u here to sort of indicate that we're talking thermodynamics. I'm using the average of the energy here to sort of imply that this is derived from statistical mechanics, but it's the same quantity, right? Just maybe as an intermezzo here, sometimes we use E. Sometimes we use these brackets for averages as well. In statistics, they are often used for slightly different types of averages, but we're not going to care. Sometimes we just use this bracket just to make it clear. In our language, they are the same. Okay. Let's prove this puppy here. First, I want to give you a few useful relations before we even start that proof. Just so that the proof becomes shorter. The first one is that the derivative of the logarithm of the partitioned function with respect to beta, that relates to the energy. Because if I take this derivative, right, the derivative of the log, that gives me 1 over q, and then I take the derivative with respect to q. And let me write out what q is, because you're going to take derivatives like this a lot of times. So q is the sum over the microstates, exponential minus beta ei. So you're often going to take derivatives of the log of q in StatMech. And it always look the same, right? So you take the derivative of the log, that makes a q come down. And then you have to take the derivative of q. And q is always the sum. And if you take the derivative with respect to something that appears in the exponential, which you're doing, right? In this case, beta, then you're bringing in energy down. So this is 1 over q sum I minus EI times exponential minus beta EI, right? I think we're losing most of the class slowly. So what do I have here? If I take this partition function, sorry. If I take this partition function and combine it with the exponential, this term is the probability of state I, right? Because I have the exponential of minus beta, the energy, divided by the partition function. So that's the probability of state I. So this is equal to sum I pi EI with a minus sign. So this is equal to minus the average energy. So what I've just proven is that the average energy is minus d log q d beta. I can do the same for pressure, because I'm going to need pressure in these equations. And I'm going to define the pressure in a microstate. And now it gets kind of messy because we have a P for probability and we have a P for pressure. So this is done better in the notes, but the average pressure, because in the notes it's simpler to define a capital and a lowercase. So the probability, the average pressure is the probability over all microstates times the probability of the microstates times, it's never going to work, times the pressure in the microstate. So this P here is pressure. This P here is probability. This pressure, right, is the mechanical pressure in a microstate, and that has to be the derivative of the energy with respect to the volume. So that means that the average pressure is the sum over all the microstates, and what you're averaging is the derivative of the energy with respect to volume. Right? So you have the probability here, and you have the pressure here, which is written as the volume derivative of the energy. Okay. I'm now ready to prove this equation here. What I'm going to do is I'm going to calculate the first term as an example, and that's already hairy enough. And then I'm going to tell you what the second term is. I'm going to let you do that at home and prove that. But we will essentially then be able to prove this equation. Okay, so let me start with the term, the derivative of the average energy with respect to volume at constant n and beta. So if I write that out completely, explicitly, that's the derivative of with respect to the volume, and the average energy is the sum over the microstates, and what I'm summing is the energy times the probability. So the reason this gets a little messy, because I have to take a volume derivative of this, and I have three terms, and there is volume dependence in all three, right? So this derivative gets a bit lengthy because the energy these are the energy levels that has volume dependence. And then of course the partition function contains them all. So that has volume dependence as well. And so that's why I'm going to get quite the number of terms here, right? Okay, so let's get started. So I'm going to do this very systematically, right? You know how you take derivative of these products. You take the derivative of the first, multiply with the other ones, take the derivative of the second, multiply with the other ones, take the derivative of the third, multiply with the other ones, right? Okay. So first I'm going to take the derivative just of this. So my first term will be sum over microstates, derivative of the energy with respect to volume, and again, then times the probability. Right, that's my first term. That one is easy to recognize what it is, right? Because this here is minus the pressure in a microstate, right? It's the volume derivative of the energy of that microstate. So basically what I'm doing is I'm averaging the pressure, because this here, this is just a probability in the microstate. So I have some pressure times probability. So this term here, the first term, we know this is the average pressure. So that one was easy. Okay, so now let's do the second term. So now I'm going to take the derivative of the exponential. So that's going to bring some stuff down. So I'm going to do the second term here. So plus sum over the microstates. I keep the energy and I keep Q, and I take the volume derivative of this term. So I get minus beta times dE nu dV times the exponential of minus beta E nu. So one cool thing that you always get, right, when you take derivatives of exponentials, you always get the exponential back. And since the exponential is our probability, you always get something that is the probability, even after you take the derivative. And that's what you see here, right? So again, I have, right, let me put the Q here, right? If I put the Q here, I always have the probability of the microstate appearing. And what am I averaging now? The thing is that what I'm averaging is a little bit of an odd quantity, right? So this here is minus beta times, sorry, this is beta times the pressure in the microstate. So what I'm averaging is the product of the energy and the pressure. So this term here is the is beta times the average of the product, right? It's not average of energy times average of pressure, right? It's the average of the product. That's why I draw the line as one continuous line. Okay, one more term. So the last term is where I take the derivative of Q. So now I get, I take the derivative of 1 over Q, so it gives me 1 over Q squared. And then I take the derivative, okay, 1 over Q squared times sum over the microstates, E nu times exponential minus beta E nu. So that term I just carry over. And then I have to take the derivative of Q with respect to the volume. So that gives me minus some new, and we've done this already, right? Beta times dE nu dV times e to the minus beta E nu. Okay, I'm going to divide the Q squared here. So I'm going to put a Q here instead and a Q there. So I can turn stuff into probabilities. Okay, so here again, I have a probability, right? This is not a naught, right? This is a E nu. So this is P nu again. I have the same here, right? This is P nu. So here I'm averaging the energy. What I'm having here I'm averaging again the pressure, right? Or minus the pressure. So what this last term is, this last term here, this is beta times the average of, okay, sorry. This here is beta times the average of E times the average of P. So this whole term is equal to minus P average plus beta times EP averaged minus beta times E averaged P averaged. Okay. I realize it's a bit painful, but do work through this. Statistical mechanics is a bit, it looks a bit messy mathematically, but the good news is that most of the mathematical operations, there's sort of a very finite set of, you take derivatives of partition functions and you take derivatives of exponentials, and you just have to systematically work through it. And we're going to do more of this, but you really have to get the practice in the bones, I would say. So please work through it. And to incentivize you, I'm going to let you do the second part. Remember, this was only one part of the equation we're trying to prove. There is, are we here again? So we just did this one, right? dE dV. But we still have to do this one, dt d beta. No, that's dP d beta, right? Sorry. I made a mistake here. That's dP d beta. Sorry. So when you do that, when you do beta times dP d beta, and you do a few pages of math, you get that this is equal to the average energy times the average pressure minus the average of the product of the energy and pressure times beta. And see how far you can take that. I think if we do it here in class, we're not going to survive. We need to get to something more fun. Okay, so I'm going to rotate the board so I can go back to what we were trying to do. So if you believe all my math, we will have proven this equation. And since this is derived from the postulates of statistical mechanics, this is derived from thermodynamics. These have to be consistent. And the way, and what you can prove is that these are consistent when beta is 1 over T. or is proportional to 1 over t. And you can kind of see this, right? You should, the way you can, I'm going to let you prove that, but you can take, there's many ways you can do it, right? You can define a derivative d beta, right? You can take, you can write as a chain derivative as d dt times d beta dt, right? And then you see that this is going to bring a 1 over t squared down. You're going to flip sign, and that's how you're going to get the difference here between the minus sign and the plus sign. Okay. So these look very similar. So you would almost think beta is equal to t, but it's not, right? Because there's a difference in sign. But that comes from the chain derivative, right? That if you want to think of it, because beta goes like inverse temperature. So beta gets smaller as t gets bigger. A derivative with respect to t and a derivative with respect to beta usually have the opposite sign in front of them, right? Because dt is some constant times minus d beta, right? So I'm going to let you figure that out. But the conclusion from this will be that beta is proportional to 1 over t. And the proportionality constant will be picked as the Boltzmann constant. So we will say that beta is 1 over the Boltzmann constant times t. And that's really a unit measure, right? That all the Boltzmann constant does is that t is given in some kind of scale, you know, Celsius, Kelvin, Fahrenheit, whatever, right? And beta is essentially an inverse energy unit, right? And that because that's the way it appears in the Hamiltonian always, right? So beta always appears multiplied by the energy, and it has to make a dimensionless number. So beta is inverse energy. And so what relates temperature to inverse energy is the Boltzmann constant, right? So if we had other units of energy, if we have other units of energy or other units of temperature, then the Boltzmann constant is different, right? And you know that, right? You can express the Boltzmann constant in terms of joules per Kelvin, but you can also express it in terms of, say, electron volt per Kelvin. Okay, let's do something more fun. Okay, so I want to now relate the partition function to the free energy, the classical thermodynamic free energy. And to do that, I first want to prove an equation that we actually haven't proven yet in classical thermo, that we always somehow seem to skip, which is called the Gibbs-Helmholtz relations. Supposed to be a line under there. The Gibbs-Helmholtz relations are that the derivative of the free energy divided by temperature with respect to 1 over t is the internal energy, and the derivative of the Gibbs free energy divided by temperature with respect to 1 over t is the enthalpy. And if you use beta, you can rewrite this sort of cleaner. It means that the derivative d beta f, d beta is the energy, and the derivative beta G d beta is the enthalpy. Okay. Let me see if I can quickly prove that for you. I'll prove one of the two. And let's just erase this traumatic experience here. Okay, if I take the derivative of the f over t, first with respect to t, so not with 1 over t, at constant volume, that's minus f over t squared, right? Because I take the derivative of 1 over t plus 1 over t times df dt. And I'll do that at constant volume. So the dt at constant volume, this is minus the entropy, right? Which you can know from the differential of the Helmholtz free energy. And then I'll multiply both sides times t squared. So what I get is that t squared times the f over t dt at constant v is minus f plus ts. And minus f plus ts, right? That you know what that is, right? Because f equals u minus ts. Sorry, I was sign. This is minus here, right? Because I get the sign from the minus the entropy. So this is equal to minus u. And I just have to rearrange this here. I'm going to take the t squared dt and turn that in a derivative of 1 over t. So this is equal to the f over t d1 over t with a minus sign, right? Because you can use the chain rule to prove that, right? With a minus sign is equal to minus u. So what we've proven here is the first Gibbs-Helmholtz relation. The second one is exactly the same, right? You just, if you stick g in here everywhere and you do that constant p, then you're going to get g everywhere. You're going to get dg dt, which is the entropy. You're going to get exactly the same thing, right? You're going to get the enthalpy on this side. So the two Gibbs-Helmholtz relations are exactly the same, basically. Okay, Jen Young, are you ready with the drum roll? Because we're almost there. We're almost to the apex moment here. I hope you queued up a drum roll. Okay, so what we now know is that d beta f, d beta is the internal energy, which means it's the average of the energy. And that's also equal to minus d log q d beta. We proved that a bit earlier. So it seems like the log of q and beta f have the same derivative with respect to beta. So if I integrate with respect to beta, I'm finding that beta f is equal to minus the log of q plus some constant, which I don't care about, right? Because it doesn't depend on anything. Or the free energy is minus 1 over beta, the logarithm of Q. Okay, do we have a drum roll? I hope that you're like not defeated so much from this whole derivation that you still have, you know, some ounce of excitement left, because this is pretty spectacular, right? We've shown that that thing that comes as a normalization, you know, Q is just the sum of the exponential of minus beta the energy states, right? This thing. That's actually the free energy, right? Well, the log of that is the free energy. So this opens up so many possibilities, right? Because in thermodynamics, we tell you that if you know the free energy, you know everything. If you know the free energy analytically, you know everything, right? Because the first derivatives are the equations of states, the second derivatives are the property. It's like the world opens up to you, right? So what I'm really telling you is that if you know the partition function, you're in the same boat. If you know the partition function analytically, right, it would be able, if you can do this sum, you know everything there is to know. And this is, of course, where the tide turns, and that's a good theory to go like, but of course, we rarely ever actually can sum the partition function. You can do it for simple models. It's done for one-dimensional spin lattices, things with a magnetic spin on them. They're trivial. It's actually, you can do it as a homework problem. In 2 dimensions, so putting magnetic spins that can just be up or down, like the Ising model as it's called, in 2 dimensions, was solved by Onsager, and he got the Nobel Prize. Go Bears, 2 in 1 week, okay? I think we're above Russia now. So, and in 3D, if you put magnetic spins in 3 dimensions, like on a cubic lattice, we still can't solve it analytically. So it is rare that we can actually solve the partition function analytically. But if you could, you know everything there is to know thermodynamically. So partition function and free energy play the same role. Well, what free energy does in classical thermodynamics, the partition function does for you in statistical mechanics. And what we're going to see, like next lectures, is that just like we have a thermodynamic potential for different ensembles, so if we have different boundary conditions, we have a different thermodynamic potentials. Well, if we have different boundary conditions, we'll have different ensembles and we'll have different partition functions, right? So here, the Helmholtz free energy is this partition function because I work in an ensemble under constant volume. If I were to work in an ensemble under constant pressure, I would have a different partition function because my states could have different volume, and I would have a different free energy. It would be the Gibbs free energy, right? It's a perfect analogy here. I'm on time. I'm actually done. I thought there was a lot left. Any questions, or are you totally defeated? Can I say, please do this derivation, walk through it? Because you need to get to this point where like the math comes as second nature to you, so you can focus on the conceptual things, right? This is why you need to study things multiple times, right? The first time you study a problem, you're annoyed about the combinatorials and the logarithms of this, and you worry about Stirling, and right, and you're way too busy to see the conceptual things going on, right? So you first need to work through the derivations, right? Because you know, it's like gene editing, right? Okay, I'm on a topic here, right? But you know, you first look a little bit at the letters, right? And after a while, you get whole blocks that mean a concept, right? You know, after a while, you're going to go, oh yeah, I have a combinatorial. I know how to deal with that. I take logarithms. I know exactly how the minimization of that's going to look like. It's always going to bring up an exponential, right? So after a while, you get that concept, and you can now put these bigger blocks together. My worry that you know, when you study at the sort of too low a level, right, you just see the little mathematical pieces, right, and you don't see the big, you know, the big picture of what you can make. And I hate to sort of keep on banging on you, right? But that's a bit what happened in the first exam, right? I think a lot of you missed the sort of bigger picture, and you were stitching like tiny little pieces together. So let's do this better in stat mech. Like work through this. You will have to, right? The next lectures are going to get very hairy for you if you haven't sort of worked through this. So tonight, I don't know, get your favorite tea or cocktail or glass of wine and kombucha, whatever, and work through the canonical derivation. You're not going to regret it, trust me. It's like a classic. Okay, get your tea ready.